begin by taking my jacket off. As I was told, the audience never takes you seriously with your jacket still on. But they wired me, so the wiring's in my jacket, so I'm now stuck. That said, okay, I get to bad cleanup. So what is this talk about? I was listening to these wonderful talks that were presented before I got up here, and I realized I should probably tell you a little bit about why I'm up here and how I got to be up here. It's a long story, but I'll compress it to only a week's length. Well, maybe a little shorter than that. I think I have a little help here. Well, that's me. Okay. We'll go for a little bit more help. And, it was supposed to work. There we go. Well, first there's a title. As a physicist, I like to use titles. So, plastics, the next generation. And so, why do I talk about this stuff? Well, in fact, there's supposed to be a movie here. Next one. Okay. Some of you are young enough to remember this movie.
Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
Enough said. That's a deal.
For those who missed the introduction to this, this is from a movie called The Graduate, which I saw in 1968. A little slow in those days. It came out in 1967, but I waited a year before I saw it. And I was actually a graduate student at that time. And it was a very moving movie. It's kind of corny now if you take it out and look at the DVD. But if you imagined you were 40 years ago, it's really meant a lot. In this movie, Ben, which is played by Dustin Hoffman, comes home having graduated from college and is very puzzled what to do with his life. And he has two major scenes. One, I'll let you rent the DVD to find out. The other one, and more important to people like me, is the one you just saw. And in case you missed it, I'll let you watch it for, it's only about 18 seconds long.
One word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
Enough said. That's a deal.
I showed this clip to a group of incoming graduate students of physics and chemistry and several years ago. And it was the last time I showed this clip. I stopped showing it because I didn't get a single laugh. And I finally, afterwards, asked some of the students what they thought this clip was about. And they said, well, we weren't sure, but we think it's a drug deal. Talk about generational change. Well, okay, so why do I identify with Dustin? Okay, there's a couple other characters in the movie. I won't tell you about those. But I do identify with Dustin because a year later, I was 1968. I was a PhD graduate student in physics, and I was working on metals. I was looking at the properties of metals in my laboratory. And I came in one day, and my mentor, who had been in Europe, had come back and left on my desk a document upside down. Now, when you see something upside down, there's usually a warning. If it was really good for you, it would be right side up. So I cautiously turned it over. There was no mousetrap, but it was something worse. It was a preprint of a paper from an esteemed lab in Europe that was exactly the research I had spent the last 4 years working on. And if you understand how a PhD works in the physical sciences, that meant I could not go forward with what I was doing for my PhD thesis. I had to do something different. So I went to see my mentor and discovered he had already left town to go to California for 2 weeks. Smart man. And so I thought about all kinds of alternatives from suicide to mentorcide. And but my wife, who's in the audience, was actually got the better part of me, and so okay, I'll wait until he comes back to town. And I did meet with him 2 weeks later, and He was very smart about it, and he said, look, it's not the end of the world. You could study another metal, and it'll be fine. You already have the experience. You know what to do. It won't take you 4 more years, maybe 6 more months. It's okay. But he said, on the other hand, I just hired a chemistry postdoc because I read some papers about some organic materials that have some interesting properties, and I wanted to study these materials. Would you like to switch fields, take the opportunity to switch to look at the new field of these physics of these organic materials? I said, let me think about it a little bit. So I turned around. Dustin. So if it was good enough for Dustin Hoffman to get the advice about plastics, then organic materials, you'll see in a moment, plastics comes together. It was meant to be. All right. So let me tell you a little bit about plastics. First of all, what is a plastic? The term plastic means several different things. In this context, I think of what we call polymers. Polymers, by its word, means poly, many. Mer is an item. And if you think of it as a string of pearls, in this case, a repeat unit here, the dark atoms of carbon. This may be another way to do this. All right. There we go. And the light atoms of hydrogen. So this is an ethylene, and this is called polyethylene. And you've all handled these squeeze bottles. And this is what common use of polymer materials are. Another common polymer is nylon. And nylon has the same types of repeat, just the atoms are a little bit different and placed in different places. In this case, nylon is used for clothing or for some important products like kites. Actually, I saw this kite in a store in China, and it's quite a pretty kite, but not wearable. It makes me think a little bit about other uses. And in fact, the other uses of polymers tend to be what we call mechanical. That use it for polyester clothing, or usually for a polycarbonate, which is plexiglass for transparent windows, which are also just mechanical. Or you could use it in many other kinds of places like bumpers. However, there's much more to life than being mechanical. And if you think about it, a good measure is how materials will conduct electricity. And the scale of electricity is in units of Siemens per centimeter. It's really not important, but the scale is very big. It varies by about 24 orders of magnitude. It's the property of materials that has the largest range of variation. And the traditional polymers, usual polymers, are materials like polyethylene and nylon, and they conduct at a range of about 10 to the minus 16 on the scale. That's even less conductive than diamond or glass. They're really very good insulators, more like quartz. What has provided a major change to society, though, is going away from just insulators to materials that conduct electricity, like semiconductors. Whoops, let's try this again. I'm sorry. Semiconductors, which are materials that are medium-level conductors, or metals, which are very good conductors. So if you want to take polymers and move them into a different area, what could one do? Well, you have to look at why do materials conduct electricity. Well, first, you may remember, so it's like a high school lecture for a moment, having an atom surrounded by energy levels. And you may have learned about this when you put electrons around a proton. They form these energy levels, and these are the energy levels that are allowed for a typical atom. If you have a solid, you may take many atoms together, and instead of having energy levels, it acts like a garage, sort of like the garage next door here, where there are many levels. And typically, you might find 3 levels that are completely filled, especially if you come in late. Then you might find 3 levels which are closed for repairs, damn it, and pardon me. And then you have to really rev up that car to get up the ramp all the way to the top to get to the empty space. So that means it's like an insulator. It's hard to inject an electron. What happens if the levels are a little bit closer together? Aha, now this one only has 1 closed level. It's now easier to inject that charge and also easier to take one out, and that's a semiconductor. And semiconductor has some cool properties, like you can easily take electrons out of them as well as put them in. Oh, by the way, I do represent the electrons as cars because it's a little easier to think about that way. And the car can, in fact, fall through the floors to fill an empty hole. Okay, we'll return to that in a moment. Okay, so how does a metal work? Not because there are more electrons, but a metal works because the top level with cars is only partly occupied. In that way, if you have a car entering, okay, why is this thing not going? Let's go up. There we go. Car comes in, shoves another one out of the way, one goes out the other side, and the same number of cars remain. This is how the copper wire works in your copper wiring works. This is how generally electricity works around your house. Okay, so we want to go ahead and make different kinds of plastics that do this, and the key to it is to use a different kind of bond. So we use plastics that bonds are made up of these what's called p orbitals. It's got to be a better way. And with this bonding here, you get a kind of small gap in these materials, so it can act like a semiconductor or like a metal. I think, and just to tell you a little bit how a car can, how the electrons actually move in these materials, the electrons will then hop from what I call pearl to pearl, or a repeat unit of a polymer to the next repeat unit along a chain, but they're kind of stuck on the chains, and eventually they hop to a neighboring chain, and they go around, which opens up then the opportunity to employ chemical engineers. Chemical engineers are some of my best friends, and their role is they take these polymers and learn to process them so that the chains line up together, so you have like almost a crystal. And then in those areas, the electrons can more easily transfer between the chains. So like have a switch yard available. Okay, let's move this quickly. You can take these polymers and make fibers. Fibers are useful. Why are they useful? You could do several things like put them into carpets, so your carpets don't give you static shock. You can put it into jackets you wear inside silos where you have, you've harvested wheat and you put the wheat grain in there because you get dust, and that dust will explode when you have a little bit of static charge. You want to discharge. But we should look beyond that. We've learned how to take our polymers and actually make what are called nanofibers. These are little fibers that stick up that are about 1 million times smaller than the fibers I showed in the previous picture. And when they organize parallel like this like a set of stalactites or stalagmites, it goes ahead and produces, must be a way to get this again, here we go, that if we have a water droplet drop down onto the sheet, it just rolls right off. It's called super hydrophobic. So a drop of water will not stay stable on that piece of plastic. Now, what else can you do with these materials? We saw this, what I call the garage theory of solids. So if we imagine our garage where we have our semiconductor again, where we have filled energy levels for three regions here, then one closed for repairs. And imagine there's a bright light shined on this. That bright light, oops, there we go. Bright light coming in is strong enough, gives enough energy to a car to lift it up to the next empty level. And so being the electron or a car can get out, and another one comes in from the side here. And that's how you use light in a solar cell to generate electricity. It's in the same process here as it is for the inorganic solar cells from silicon or cadmium telluride. This can actually be produced, and it's now produced commercially by a company called Canarca. I don't have any ownership of this company. They haven't licensed my patents. It's just a very nice photo, and they're, I think, one of the first companies to commercialize these polymer solar cells. You might ask, why deal with these polymers? The answer is not because they're so much more efficient. They're not as efficient as traditional solar cells. What makes them cool is that they're flexible. And because they're flexible, you could wrap them on a tent. You can wrap them on your bag. You can put them on the back of your knapsack easily. And you collect power wherever you happen to be. Okay. The other thing you can do with these semiconductors is imagine then having putting charge into the system that's having these extra electrons come in, and then they go into the empty level on here, and they'll fall through the opening to an empty space down below. How far it falls determines the color of the light that comes out. So these plastics will then give off light of different colors. Here you see a green light because this opening where it's closed is smaller. If we make it even closer together, which is controlled by the chemistry, then you get a red light coming out. So you can tune it to emit red, blue, green. You can also do yellow and other colors. So where does one go from there? Because they're polymers, we can actually dissolve them in a solvent. And here you see a red, a green, a blue. And you can take those and put them in the wells from the inkjet printer menu you have on your desktop. And then you can use the inkjet printer to print these type of dots. You can put those dots in a periodic array, and you can then do things like make these television sets, which are these ones are actually prepared by Sony in Japan, but they're made by the same process we described here. These have the advantage over liquid crystal flat screen displays that usually you see now, in that you can look from an angle like this and still see a bright picture, whereas the liquid crystal displays, you have a parallax issue. When you look at an angle, you don't see the display. Okay, let me go into another area. So we show that plastics now are not just insulators, they're not just conductors, they can be super hydrophobic, they also can be electronic, they can be used for light emission, they can be used for light absorption in a solar cell, but you can also control the chemistry to turn these materials into a magnet. So you can make these plastics magnetic by adding by organizing it so that you have an odd electron in each of these molecules, and the odd electron does interesting things. The odd electron has something called a spin. We can think of the electron as spinning like a top, and if the spinning like a top, if all the spinning electrons are pointing the same direction, that's called a ferromagnet. If they're in random directions, it's called a paramagnet, and if they're alternate up and down, we call that an antiferromagnet. Okay, so let's look a little bit about this. How do we actually make that? This is a picture of a spinning electron, and the arrow indicates it's going around clockwise if I put my hand around it. This is the molecule we really use to make it. Why do we, whoops, now doing something funny. Okay, here we go. My student actually went and prepared this material in the glove box, and this is a sheet of Teflon on which we coated this plastic magnet. And you see the sheet itself does not move when you just put a piece of stainless steel near it, which is non-magnetic. On the other hand, if she brings along a magnet near it, I think it should come back. Where is it? Yes, that round ball is a magnet. That sheet comes right to the magnet. So you can make this material into a magnet, and the magnet in turn can be used in several different ways. And one way I'd like to talk about is an item that many of you played with as youngsters, I think. At least I used to play with it, and that is sunglasses. If you have Polaroid sunglasses, Polaroid sunglasses were very good at taking light in, whoops, and the light would come in on the upper left and go what looks through from Venetian blinds, actually be strips of parallel polymer chains, and would come through and be green. And if you took a second pair of sunglasses and put it next to it, you get the green light going through further. But if you turn that second sunglass 90 degrees, it turned black. Okay, so where do we go from there? Can we do something else similar for that with magnets? So we take our Ohio State Buckeye team, which is not doing so well this year. Well, sorry about that. We have here an electron. This is going a little faster than I expected. We have here a doorway, which indicates it has magnetized and it has an arrow up. And our soldier goes through it with an arrow up. An arrow up allows an arrow up to go through. If he gets to a doorway where there's an arrow down, he can't go through. If, on the other hand, he passes into a doorway where there's an arrow, we'll try it again, where there's an arrow up. Okay, this is it. And now he got through that one, and then he goes to the next doorway. Sorry about this. Pass this fairly quickly. Last try. Okay, he passes through one doorway, and he goes to pass the second doorway, and the green arrow indicates he can go through the second doorway if the second doorway is pointing the same way as the first doorway. And this is a graph that shows, in fact, this is how it works. if you have a piece of polymer, all right, then if the doorways are aligned the same way, we have a low resistance. If we apply a magnetic field that switches one doorway to be the opposite direction, we get a high resistance, the resistance goes up. If we had a lot of time, I'd teach you about this using quantum mechanics and field theory, but I will pass doing that. Okay, what else can you do with these organic materials? Because they're organic, you can do fun things with them, like shine light on them. You shine light, the light gets absorbed and changes the magnetism. You can't do that with conventional magnets. And finally, I want to turn to an area to do with the magnetic and the electrical polymers for other kinds of uses, as in medical applications. And one area I want to talk about is for glucose sensing. It's one developed by a graduate student and myself recently in our laboratory. And it's a very simple concept. Many diabetics have to measure their glucose level daily, have to measure it several times a day, and they normally do that by pricking the skin and taking a little bit of blood and looking at this with a simple detector. That endocrinologists tell us they have to do that many times a day, and they don't have very good compliance in people doing it. So we came up with a very simple model of taking our polymer that normally you use for conducting electricity, and if we bring into it an enzyme which is in everyone's body, glucose oxidase, that enzyme will interact with glucose, and when it interacts with glucose, it takes a hydrogen from the glucose, and the hydrogen comes off and goes over to the polymer, and when that happens, an electron also goes by, and it changes the electronic structure of that polymer. The bonds change. And when that happens, then the color of the polymer changes. And so you can actually use that change in color of the polymer from blue to yellow to actually measure the amount of glucose that's available in the bloodstream. So the very simple concept there, okay, let's on the next slide. The very simple concept is that is to take the polyaniline, or this polymer, with glucose oxidase in it, put it on a reflective surface, so the green represents this polymer. The black is actually a reflective surface, a piece of like aluminized mylar, and place that underneath your skin in what they call the interstitial fluid. And then have a detector like your watch. On the back side of that watch, you have a photo LED, which itself will produce light of the right color to probe which color polymer it is, yellow or blue. And the other item here is the detect looks at that reflectance. So we've seen yellow reflectance or blue reflectance. And from the balance of the two of them, you can determine about the glucose level. And what excites us is that this kind of technology will give you a continuous monitoring. It's optical. It goes through the skin and looks at the reflectance back through the skin. And it's at a wavelength that does not interfere with by the skin. And so the idea there, you use that to then give information to be stored on a computer or chip, or even broadcast wirelessly to an insulin pump. So it's hopefully it can help the problems of people with diabetics. Okay, let's move forward just a little bit here. There's a lot more we can talk about, lots of other kinds of applications that are new and different, but I do realize it's getting now pretty late. So I think it's probably a good time to just give something larger view of things. That first of all, the idea of plastics has changed dramatically, and it's no longer simply chemistry or chemical engineering, but now it brings together physics with chemistry, biology, and medicine and engineering, where you can control what the pearl is that makes a chain of the polymer, and you take those pearls and you do things to make them more functional. You can make them give off light, it will absorb light. You can make them have medical functions, you can have magnetic functions, and they still remain strong and have other good properties as well. We're using some versions of these as new ways of measuring mammography, and we're doing other kinds of fun things with these as well. Okay, I think there's only one slide, and it's one to say that I have a collaborator who unfortunately passed away, a wonderful man, Alan McDermott, and he expressed much of how I feel about science. It's a very simple phrase: science is people. And that is, if you are going to do any research, any science, you don't do it alone. You have to talk to people, you have to be with people, you have to collaborate with people. And science indeed is people, and you go around the world and you interact them, and it's just great. I also want to thank in particular, among the people listed here, my collaborators, some of the students by name. This is my group here. But especially want to thank Terry Bradley, who put up with me at being late and getting her some drawings we needed done for the animations, and she did a great job. And I want to thank our funding agencies. In particular, I want to tell you about two kinds of funding agencies from the NSF, one called an MRSEC and one called an NSEC. Those are two interdisciplinary agencies that are funded to have people from different departments work together on complicated problems, and that's a very important thing these days. And last and not least, I want to thank my family and thank them for allowing me to have so much fun doing my research and educating students. Okay, and thank you for your attention.